Uh, Good morning. This is Professor David J. De Los Reyes, an electrical engineer by profession, and also as an electronics troubleshooter. I've got so many experience on the troubleshooting of electronics, hands-on. Okay, let's proceed. My lesson this morning will be lesson number 97 on my channel on the topic integral calculus. The subtopic on the integral calculus is surface of revolution. And for this morning, the object that we will be deriving a surface area will be a sphere. Sphere, like the globe or a basketball, something like that. The total surface area. Okay, I will try to read the problem. Derive by integration the total surface area of a sphere if the radius of that sphere is radius r. Okay, let's try to bring out the figure on the Cartesian coordinate system. This should be the figure. Okay. On the Cartesian coordinate system, this will be the x-axis, this is the y-axis. A sphere got a radius, right? So we will draw a circle around in which the radius is r. Okay. Then since this is a sphere, if we try to figure out, it got a skirt at the middle like the equator of the earth. Right? The equator of the earth. This is the equator. And there was actually a surface area also at the back. So I place it as a dotted line. The problem is asking if the radius is r, how much will be the total surface area? Total surface area for a sphere is actually 4 pi r, okay, square units. It should be square units. Oh, an erratum from my previous lecture yesterday under 96. I placed that the unit of a surface area is just simply unit. Sorry for that one. That's I will correct that one. The unit for a surface area will be square units because it should be the product of a unit length times a unit length. So it should be a square unit length. So from my previous lecture yesterday under 96, I think the total surface area of a right circular cylinder, I will correct that one now. You might be criticizing me for placing the wrong unit. Okay. Yesterday for a right circular cylinder, the total surface area is actually 2 pi r times h. This should be square units, guys. Okay, these should be square units. That is for a right circular cylinder. I placed it wrong yesterday. I just placed it units, but supposed to be, it should be square units because the product of a unit length times a unit length will be a square units. Okay. Oh, that's the only error yesterday. It's in the writing of the total surface area. It should be square units. Okay, for a sphere, the total surface area, if you try to Google it, it is actually 4 pi times the square of the radius, square units. It should be square units, guys. A unit length times a unit length will be square unit length. So if it is inches, it should be square inches. If it is meter, it should be square meter. Okay? It should be square units. Okay, let's try to derive this one. Actually, this formula was derived by using integral calculus. The formula for taking the total surface area of a sphere under lower mathematics is actually 4 pi square units, and that actually originated from integral calculus. It was derived from integral calculus. It was derived using integral calculus. Okay, let's proceed. We will use symmetry over here. we will draw a horizontal slice. Okay. Then this horizontal slice, we try to rotate this one complete revolution with respect to the y-axis. Okay, so I'm using a horizontal slice, and that horizontal slice is to be rotated with respect to the y-axis. So if you try to unwind the surface area after the rotation, it will be something like this. Okay, the circumference will be 2 pi x, and this length here is actually differential arc. This arc over here, this is the arc. Okay, let's try to bring out the solution. Actually, the total surface area, if we try to rotate it with respect to the y-axis, this will be the formula. It is this one. Okay, so actually it is 2 pi times the radius times thickness, where the radius is x and the thickness is ds, small ds, the length of arc over here. That was our previous discussion, length of arcs. That's why before proceeding with this, I computed first differential length of arc separately. Okay, differential length of arc is actually the square root of 1 plus dx over dy quantity square times dy, equation number 1. This is one of the general equations, okay? It could be dx dy or it could be dy dx. But if this is dy, this should be dy. If this is dx, this should be dx. Okay, equation number 1. Since we are considering a sphere for the meantime, we will derive the relation of x and y from the resulting equation of the sphere. And since the equation of a sphere is actually the equation of a sphere, is x squared plus y squared equal to r squared. That's the equation of this. How it varies? It is actually quadratic. Solving for x over here, x squared plus y squared equal to r squared. X squared will be r squared minus y squared. X will be the square root of r squared minus y squared. Okay? So we are now given x as a function of y. And we need to compute for dx over dy. Dx over dy now equal to, take the differential of both sides. This should be one power formula. 1/2. The value of u raised in power by, decrease in power by 1, this is negative 1/2, times the value of dy inside. It should be 0 minus 2y. Dx over dy will be, actually here, this 2 here cancels. Okay, so what remains will be dx dy equal to negative y over the square root of r squared minus y squared. That's the first derivative of x with respect to y. Squaring both sides. Dx over dy quantity square equal to, the square of negative y will be y squared. The square of the square root of r squared minus y squared will just be simply r squared minus y squared, equation number 2. Okay, then I will try to take the value of equation number 2, I place it on equation number 1. Differential length of arc for a sphere, okay, will be equal to the square root. I am just following this. 1 plus y squared over r squared minus y squared, all multiplied by dy. Simplify the 1 inside. 1 times this will be r squared minus y squared plus y squared all over the common denominator r squared minus y squared. Okay? And luckily the 1 inside y squared cancels. Okay? Then the square root, the operation inside the radical is division. So actually we could take the square root separately. The square root of r squared is just simply r. And the square root of r squared minus y squared will be the square root of r squared minus y squared times quantity dy. Equation number 3. Meaning the differential arc for a sphere, okay, the length of arc for a sphere will be the r, the square root of r squared minus y squared times dy. Equation number 3. Okay. Why I mark this as equation number 3? Later on, I will take this value, I will place it here. Okay. So, taking one of the cases under the so-called surface of revolution, if we try to rotate the surface area with respect to y, the differential surface area with respect to y. The subscript y refers to that the surface area is to be rotated with respect to the y-axis equal to 2 pi times radius times thickness. The radius of the differential area is actually x. This is x. Radius is x. Thickness is ds. And what is ds? ds is actually formula number 3. The one we derive using equation number 1 and number 2. Okay? So I place it here. Differential total surface area with respect to the y-axis equal to 2 pi times x times thickness. Thickness is equation number 3. So I could go back here, I place it in. So this should be r dy over the square root of r square minus y square. If you notice it, the variables here are y, right? And this is x. So there is a difference. So to integrate this one, it's either we replace y by x or we will replace x by y. And to simplify calculation, we should compute for x as a function of y. X as a function of y. And where do we get that relation? It's still from the equation of the sphere. Since x squared plus y squared equal to r squared, that's the equation of the sphere, right? We compute for x, it will be the square root of r squared minus y squared. So what we will do, we will get this value here, then put it there. Right? So the differential total surface area with respect to the y-axis equal to 2 pi times x. It will be the square root of r squared minus y squared times the quantity r dy over the square root of r squared minus y squared. And luckily, this radical thing here cancel with this. Okay? We are just lucky. So the differential total surface area rotated with respect to the y-axis equal to 2 pi, okay, 2 pi r dy. Okay? It is a simple differential equation now. We are just lucky for us there. Okay, let's try to bring out our upper limit. Upper limit will be r, lower limit will be 0. How is that so? To compute for the total surface area of 1/2 of the sphere, the one at the top, r should move, or y should move from 0 to r. So our lower limit is equal to 0, upper limit will be equal to r. Okay? We rotate this one complete revolution, and if the range of y is from 0 to r, we are taking 1/2 of the total surface area. So to take for the total surface area, okay, we will integrate this one, okay, but we will place this one as from 0 to r, but we multiply this by 2, the right hand side by 2, to get the total surface area also, the bottom portion. So there is a factor 2 over here. Okay, so total surface area rotated with respect to y is 2 pi r times 2. Okay, using symmetry, the integral from 0 to r of dy. The integral of dy, easy money guys, it is just y. So this should be 4 pi r. The integral of dy is just y, so this is y with the limit from 0 to r. 4 pi r times the quantity, upper limit is r, lower limit is 0. Or we could remove the lower limit, it has no effect on the total surface area. The total surface area rotated with respect to the y-axis, that's the meaning of this subscript here, equal to 4 pi r squared. The unit guys should be square units. My error yesterday, I just placed it as units. Sorry for that one. It should be square units. A unit length times a unit length is actually square unit length. So this should be square units. If the radius is inches, this should be square inches. If the radius is meter, it should be square meter. But in general, total surface area of any sphere, if we are given the radius, it should be 4 pi r square units. That's it guys. Final note, total surface area for a sphere will be 4 pi times the square of the radius, square units. Good afternoon, Los Angeles.